Okay, I've started recording now. All right, I'll start. So before I start with the question one, I just wanted to quickly. So everyone can see my PowerPoint, right? Devasis, are you able to see my slides?
Yes, sir. We're able to
Okay.
see you.
All right, I'll start right now. Okay, so before I start with all the questions, I just wanted to maybe clarify a few, fundamental things. One thing I wanted to clarify. So I saw people having problems with ideal voltage sources and ideal current sources. So I thought I'll clear that up first. So whenever you get ideal voltage source like this, for example, the one I've shown here, let me just try to put the annotate here. So whenever you have ideal source like this, so let's say these are the two nodes which are given to you. So you're going to put a circuit here, you're going to get some voltage and a current is going to be drawn or sourced into it, right? If I draw the IV characteristics of this source here, so if this is the voltage across these two nodes here, right? So this is the voltage across these two nodes here, then the current drawn or sourced out of that can be anything, the voltage will always remain constant, right? So that's like the IV characteristics of an ideal voltage source. When I give an ideal voltage source, that means that voltage source can draw or source any amount of current, the voltage across it will always remain the same. But in reality, obviously, you have some source resistance, a little bit of source resistance, let's say RS. So this curve will actually, kind of change to something like that. And this will be your value V naught over RS, and this slope is RS, right? So that's the ideal voltage source. And the same for an ideal current source. If I give you ideal current source like this, and do this all the time, kind of annoying. Yeah, so if I give you an ideal current source like this, then you're going to put this in your circuit, right? Again, any voltage you apply here, no matter what voltage you apply across these two terminals, the current which is drawn out or sourced into it, this current I, is always constant, right? It's always constant. Again, but in reality, you usually have some impedance of that current source. So let's say this is also some RS. Then this won't be constant, but when I change the voltage, obviously this current is always constant. So you will get I naught, so that's I naught plus this current here, which is V over RS, right? So as you keep increasing your V, your current also will increase. So your slope will kind of look like that. And this slope is obviously the impedance of your current source, which is RS, right? So that's the ideal current source. Now, another thing I wanted to clear about is potential and current. So again, when I ask what is a potential of a certain point, like if you remember your electrostatics, so let's say you have a system of charges like Q1, Q2, Q3. So there is a field here, right? And then if I have a charge at infinity, for example, some Q, and I bring it to some point, let's say that point is some V1. So when I say this potential is V1, it's actually the work which I did, Q times V1, to get this charge from this to this point. But in a circuit, usually you never get it from infinity. You usually go from one point to another. So like you'll go from a point V1 to V2. So when I ask you what is the potential of a point, that question is usually incomplete, right, in a circuit, because your question should be with reference to what? So if I say, oh, what's the potential in V1? Then your questions should be with reference to what? So let's say I have a point V3 here. Then if I ask you potential of V1, then I say, okay, with reference to V2, then that potential is V1 minus V2, right? And if I ask you the potential V1 with respect to V3, then this potential difference is going to be V1 over V3, right? So it's always with reference to some other potential point. So you have to make clear. So it's always a branch. So you cannot, when I saw node V1, a lot of people like wrote the KVL where they would write, VB plus V1, VR1, and then they'll write V1. But this is, meaningless because it's just a node. There is no branch voltage here, right? It has to be with respect to something. Now for current, when you have a current doesn't need a reference, right? In the way the current is defined is like if you have a cross section like this, and the way you define the current, like the current density or I, is you're trying to find out what's the amount of charge which is flowing through some unit time, and that's your I, right? And this doesn't need a reference. You just, any point in your cross section of your wire, you just find a current and that's your current. But with potential, you always need a reference, right? Okay, so everyone is with me, right? So let me go solve the first, I guess this is the second one. All right, so from this question, what I was trying to get is when I write a voltage, you need to know, again, with reference to what, right? So that's why the first part of the question I ask V naught with reference to the positive node, right? I do this all the time. Okay, so I'm asking this node potential, but with respect to what? Like I said before. And the first question I ask is with respect to this positive terminal, which is the same terminal as this, right? And this terminal, again, I ask you the potential of this terminal with respect to the negative voltage. Like for example, if you just have a battery, we say it's a 9 volt, but it's 9 volt of this with respect to this terminal here. But if I take this as my reference node, then it becomes minus 9 volt, right? This voltage is with reference to this is minus 9 volt. Okay, so in order to find that voltage with respect to any node, this is one loop. There is just one loop. So the easiest way to do is you just find the current through this loop and find this voltage drop across the two resistors, and that should be enough, right? Because this node voltage with respect to this is nothing but the negative voltage of this VR1. This node voltage with respect to this is nothing but the voltage across VR2, right? So in order to find VR1, this current which is flowing in, and again, there's only one branch in this, so that means there is only one current flowing through this. So let's say this current I is the battery voltage 9 volt across these two terminal. And then if I take these two series resistance over here, that's 1K plus 2K, that's 3K, so that's 3 milliamp, right? So you have 3 milliamp flowing through this, and VR1, the voltage across this resistor here with the potential convention like I've shown here, plus 1 here, is nothing but 1K times 3 milliamp, and that's 3 volts, right? And similarly, VR2 is nothing but 3 milliamps times 2K, and that's 6 volt. So you got 3 volt here, 6 volt here. So the first part of the question is, what is V naught with respect to the positive terminal, and that's nothing but minus VR1, right? Because the way I defined here, VR, the voltage across R1 is this is positive, this is negative. That means I've defined the voltage this node with respect to this, but I'm asking it the other way around. I'm asking what is this node with respect to this, but that's nothing but minus VR1, and that's minus 3 volts, right? So that's your first answer. And the second answer is pretty straightforward. So what is V naught with respect to the negative terminal? And that's nothing but if you see this V naught with respect to the negative terminal, that is this node here, which is the same, that's nothing but just VR2, which is 6 volt, right? So that's really what I wanted to emphasize here, that, that same node is minus 3 volt with respect to the positive terminal and 6 volt with respect to the negative terminal. So I saw a lot of people writing the KVL as V bat minus VR1 minus V naught minus VR2 equals to 0. So this is not a branch, it's just a node, right? That's clear, right? Okay, so let's go to the next question. So do you have any questions so far, or should I just go on?
Yes, you can proceed.
Okay, so yeah, just mute the microphone. So the next question, again, it's a pretty straightforward question, but I wanted to bring out that first point I made, that if you have a current source, like for example, this current source, this is the ideal current source, right? So no matter what the voltage across this is, the current through this is always 1 milliamp, okay? And same thing about the battery source. So I saw a lot of people saying, oh, this battery source I equals to 0. No, this I can be anything. The voltage across this is 5 volts, right? But the current flowing through it can be anything like what I showed in the first one. So this one again has one branch, right? And the current is also known a priori, because if you look at the KCL at this node, if this is 1 milliamp, then this has to be 1 milliamp too. This has to be 1 milliamp, which means 1 milliamp has to from here, 1 milliamp has to source in here, and 1 milliamp flows through the resistor as well, right? Sorry, I saw the wrong direction. Yeah, so that's the correct. And so if the current is flowing in this direction, this voltage is 1. So if I write again VR1, the voltage across R1, it's nothing but 1 milliamp times 1K. So that's just 1 volt here. And this direction is again 1 volt here. So if I write the KVL, that's V bat minus VR1 minus VI minus VR2 equals to 0, right? Which is 5 volts minus 1 volt is equal to VI, which is equal to 3 volts. And circuit like this, you should do this quickly by inspection, because once you know the current, you say, oh, this is 1 volt drop in the same direction as this, so this is nothing but 5 minus 2 here. So once you start doing a lot of circuits, you should be able to do this by inspection right away. Okay, so that's all I wanted to sort of bring out in this question. Okay, so before I go to the next question, just quick introduction on superposition. So superposition is pretty it's really a, if you can say, whatever the extension or corollary of a linear system. So if you have a linear system, let's say like H here, and it's a multiple input, one output system, for example, then if you give a set of inputs, let's say X1A, X2A, and so on, and you get YA is your output, and you take the same system and again gives a different set of inputs, X1B, X2B, and so on, and you get YB, basically by superposition principle, which is again extension of linearity, is that if you add these two sets of inputs, whatever you get before, then you should be able to add the outputs as it is. So if you know this output, you know this output, you don't have to derive the whole function again, you just add them up, right? So that's really what superposition principle is. Now, the electrical example of that is if you have a system and you have two inputs to it, then you can give one input, make one other input 0, then go to the second set where you make the other one 0, then give V2, and this is nothing but the first set with V1 0, second set 0 to V2, and if you know the outputs of those two sets, you just add them up, right? So it saves you a lot of times rather than writing node equations and doing matrix solution. You just quickly add superposition solutions for it. All right, so okay, actually one thing I wanted to point out is if you'll see in each question, maybe I should go back to each question again. Okay, so the first question, if you see here, let me just, sorry. Okay, if you see right at this bottom corner here, it says 2 by 11. So essentially, I'm just showing how many people actually got it right from 11 people. So actually, only 2 people got it right from 11 people. Now there is a fraction here because I was giving fractional sort of grade. So so that tells you, and that's why I'm spending so much time because I was expecting pretty much everyone getting this. So maybe it's semantic. So we can discuss that later in the end. So this one again, some 3 people out of the 11 got it right. Okay, so superposition actually lot more people got right, which is good. About 5 people out of 11. All right, so to solve this by so again, I think some people actually solved this by solving the entire equation here, but that was not really my goal of this equation because I wanted you to use superposition because yeah, this is a simpler circuit, so you'll be able to just solve directly with V1, V2. But once you get more complex circuits, if you can use superposition, it helps. So let's take the first one where we'll make V2 equals to 0. And so anytime you're making independent sources, if it is a voltage source, right, if you're making it 0, then it's a short, right? You just short the voltage source. And if it is a current source and you're making it 0, because I equals to 0, which means that this is open. So this will be open. So remember that. Anytime it's a voltage source, you may short it to make it 0. If it is a current source, you open it to make it to 0, right? So V2 equals to 0. That means this voltage source, whatever was that V2 node, that is shorted. And here we are taking the reference to be ground, right? So whenever I draw a ground like this, then every node voltage is reference to this ground. Like in the first problem, I said, oh, what is V2 with respect to what node? Because there I did not have a reference node. So reference node is an arbitrary point. I can take the reference point as V2, then everything becomes, this will become minus V2, this will become V1 minus V2, and so on. So we always take something which is convenient. Unless it is connected to the mother earth, then, that has to be the ground. So when I say V2 equals to 0, that means whatever voltage source was here at V2 with respect to ground, that is shorted. So which means that this node is ground, right? So your circuit is going to look like this. So this will be ground, that's R2, R1, and this node will have R2, and you have, sorry, the diagram is not very clear, but I think you get the picture. So this is R1. So now, again, you can use node equations and solve it, but here, since you're familiar with op-amp circuits, I'll use a standard op-amp circuit result here. But before I do that, I have, because if you look at this one, this is actually a non-inverting configuration, but the voltage is not directly at, so this is the negative, this is the positive terminal. So the voltage is not directly here. So let's say the voltage here with some Vx, right? So this node voltage, I'm going to call it Vx. So I know the transfer function V out over Vx, right? So V out is nothing but Vx times 1 plus R2 over R1. Again, you can write the whole node equation, but I'm going to just use the result because I know it's a non-inverting configuration. And since this is an ideal op-amp, there is no current going into the op-amp, two-input op-amp. So if I just look at this network here, that's nothing but R1, R2, and this is ground, this is V1 and Vx. So this is R1, this is R2. So Vx is nothing but R2 over R1 plus R2 times V1, right? And I take this, substitute it here, and if you, so what is this, R1 plus R2? So if you do, then so let me call this V out 1, because I have one more source left. So this will be V1 times R2 over R1, right? So that's our first result. So for the superposition, so that was one independent source you made 0. Now you make the other one 0. So you make V1 equals to 0, and then find what's V out, let's call it V out 2 over V2, right? You want that. And again, I'm going to use a standard result, because if you make V1 equals to 0, so if you make V1 equals to 0, this gets grounded. This is grounded, which means that Vx is also ground, right? That's 0. So basically that configuration turns to simply an inverting configuration, which is R2, R1, V2 here. And let's call this the second result VR2, and that's nothing but V2 times R2 over R1, because that's minus V2 times R2 over R1. That's because it's an inverting configuration. So that's your second result. So you add these two, so your total V out becomes R2 over R1 times V1 minus V2, right? So with superposition, you can, get results quicker, and you have more intuitive feel too. So you know how Vx is getting, V1 is getting transferred to the output, and how V2 is getting to the transfer to the output. So that was the first part of the question. So I think in the second part, all I'm trying to see is identify this. What is this? And it's nothing but a differential amplifier, actually. So a lot of times, if you want a differential amplifier, differential to single-ended amplifier, using a just one op amp, you can actually use this technique, right? Okay, let's go to the next one. All right, same thing again. We'll use the superposition, so I'll just maybe quickly go through it. But this had like two parts to it, actually 3 parts to it. So use superposition like we did before to solve it. Then find Thevenin's and Norton equivalent, which are again two very important concepts, which I think you should know pretty well. Okay, so superposition. So I'm going to go, sort of introduced it in the last one, so I'm going to go quickly through this. So again, you have two independent sources here, right? So you got one. So you don't do anything with dependent sources. Now, obviously, in these questions, I haven't asked any dependent sources. In your next assignments, you'll see a lot of dependent sources. So you have two independent sources. So you start with one. So let's start with the first one. Doesn't matter which one. So we'll make I1 equals to 0. Now, when I just said I1 equals to 0 means the current source is what? Open, right? So if that's open, then this just reduces to that. You have 10 volts here, 10K, 10K. And so basically I'm asking what's the, voltage across these two nodes here, which is basically V1 minus V2. And this one is simply 10 volts, 10 volts over 2, because it's 10K over 20K, and that's 5 volts, right? So that's your one data. That's like Y1, right? So now let's find the second one. And this is, I'm assuming a direction, which is this is positive, this is negative. You can, assume the other way too, that's fine, but you just arbitrarily choose one, and, because I have my VBAT in this direction, so I'm just choosing that direction. So now we'll make VBAT equals to 0. That's the battery voltage equals to 0. Now for a voltage source, what is that? That's a short, right? Like as you said before, that's a short. So if that's a short, then you have 10K here, and then you have the current source in this direction, which is 0.2 milliamps, and then this 10K here. And I want to find out this voltage again, V1, V2. And V1, and I'll assume this polarity, and this V1 minus V2 is nothing but the current flowing through this resistor here, which is R2 here, right? And it's actually in the the current is in the opposite direction here because this current is flowing down. I've shown the, so which means that this is equal to minus of VR2, and I'm not going to solve the node equation because the impedances are same on both direction, and I have 0.2 milliamps, so which means that there's 0.1 milliamps flowing through this 10K, there's 0.1 milliamps flowing through this 10K, so that's minus 0.1 milliamps times 10K, and that's minus 1 volt, right? So V1 minus V2 by superposition is 5 volts minus 1 volts, that's 4 volts, right? So that's your, what I call it as the open circuit. When there is no load, that's the voltage across it. Okay. So the next part is I'm trying to find the Thevenin equivalent of this, right? So Thevenin equivalent, I think you all know. And again, you use that tool a lot of times. So that's something, if you're not familiar yet, you definitely need. So if you have a linear network, like some network here, and you have basically two terminals over here. So the Thevenin network is simply a voltage source in series with that voltage source, the same two terminals. And this voltage is usually called V Thevenins or the V open circuit. Well, open circuit in the sense you have these two terminals open, like without loading it, and find out what the voltage across it is. And that's the value of that voltage source. And that's your Thevenin resistance. And in order to find that Thevenin resistance, you make all independence 0 inside and find the impedance of that node, right? So that's how you find it. Okay, so the VOC we already know from the last equation, right? That's 4 volt. We've already calculated it, so we don't need to calculate that. For the RTH, like as I said, you make all independent sources 0, right? Independent sources equals to 0. Oh, by the way, so yeah, 6 people got right on this one. So I think everyone knows about this one. So I'll probably go quickly on this one. So all independent sources 0. So the voltage source becomes 0, and you had a 10K resistor here. The current source here is open, and then you had another 10K resistor here, and you're trying to find out this impedance, and that's nothing but 10K in parallel with another 10K, which is 5K, right? So this RTH is 5K here. So that's it. That's your Thevenin's equivalent, right? Okay, so the Norton is, it's a dual of Thevenin. So a dual means it's not opposite, it's the same. So a lot of times, what it means is that you can replace the network with a Norton or Thevenin, and you should get exactly the same result. Otherwise, the network is not correct. Sorry. Okay, so same thing here. If you have some linear network here, and you're trying to find out the Norton equivalent of these two ports here, it's a current source. Let me keep this direction just to keep everything, which we call the short circuit current source, and then there's also impedance across it, right? And so these two nodes represent exactly the network. If it's a linear network, and it may have dependent sources, it doesn't matter, but it might have multiple independent sources as well. And this impedance is actually the same, because that's, again, when you make this node 0, then that's the open circuit impedance looking to that node. So that's the same RTH which we calculated before, which was what, 5K, right? So we need to find this short circuit current. And I saw a lot of people make one mistake. I'll point out that is that in order to find the short circuit current, again, you have to use the superposition principle, because you have two independent sources, right? So let's make V1 equals to 0 first. So if you make V1 equals to 0, then the voltage source is shorted. You get 10K. and sorry, so you get 10K, and that's your 0.2 milliamp source. And then you get another 10K here. So that's your network, right? Now, you want to short these two nodes here, and let's choose a direction. Let's choose this as the direction of the current we want to find out. So let's first find the first short circuit current, SC1, let's say, right? So what I saw some people make the mistake is actually they calculated this current to be actually 0.1 milliamps and this, but there cannot be any current flowing through this if this is a short circuit, right? Because if you look at the KCL, then this is in parallel with this 10K is in parallel with this, but then I have a 0 ohm in parallel to this, right? So if you have a 0 ohm, nothing flows in this resistor, nothing flows in this resistor, all this current goes through this, and since I've chosen this direction, but this current is in the opposite direction, this is equal to minus 0.2 milliamps. And if you chose this, the other direction, then this should be positive, but stick to one. Just arbitrarily choose one. Doesn't matter which direction, right? I'm sorry. Actually, on this one, I've shown, okay, let me be consistent here. So let's choose this one in this direction as well. So that's your first current there, right? So the first second current, we choose I1 equals to 0. So in that case, it'll be V bat, which is 5 volts here. You get 10K, you get another 10K here. The current source is open. These are the two nodes. Again, so that's 10K, that's 10K. And these are the two nodes I shorted, right? Again, I'll choose the same direction because we want to keep it consistent. So when I short this 10K is out of the picture. That means this current is the same current flowing through this resistor, which is, so let's call this ISC2, and that's nothing but 5 volt by 10 milliamp, and that's 0.5 milliamps, right? I'm sorry, I think was this a 5 volt or 10 volts once again? Oh, sorry, this was 10 volts. Yeah, every time I change slide, I have to do this. Okay, sorry, this is 10 volts. So that's 10 volts here. So that is 1 milliamp. So this short circuit current, by superposition, I add these two. So this is 1 milliamp minus 0.2 milliamps equals to 0.8 milliamps, right? So that's the Thevenin, the Norton equivalent. So you have a Norton equivalent where you have a current source flowing in this direction with 0.8 milliamps. You have this impedance, which is 5K like before. And like as I mentioned in the second question, the fourth part of this question, since I mentioned it's a dual, I just wanted to sort of quickly show that by putting a load. Oh, by the way, I just wanted to mention that some people, they derive the Norton from the Thevenins, which is a smart way to do it, but that's not exactly what I wanted. I wanted you to do the Norton from the main circuit. So they did the Thevenins, and then they just say, oh, I'll do the short circuit from the Thevenins, which is, yeah, correct way to do it. But so only 2 people got out of 11 got it right on this one. And like I said, it's just simply trying to prove that it's really a dual. So the Thevenin, what did we calculate? This was 5K. This is 5 volts, right? I'm sorry, this was, I think we calculated this to be 4 volts. So the question was, if I put a load of 5K here, what's the current through this, right? And so this I is nothing but this 4 volt across the series resistor, because there's only one branch here. So that's 10K, that's 0.4 milliamps, right? So let's see if we get the same thing with the Norton. So we had a Norton where we chose, what is the direction we chose? Yeah, I think it's in the, so we had 5K, and this was, we calculated 0.8 milliamps, right? So that was our Norton equivalent. And so if I put a 5K resistor here, again, this is pretty simple because I have two equal resistor. That means there will be 0.4 milliamp in this branch, 0.4 milliamp in this branch. So this I is also equal to 0.4 milliamps, right? So that's all I wanted to prove in this, that they're really duals of each other. So you can use one against the other, and you'll see, some circuits you would like to use the current source. Like for example, if you have a low impedance node going in, then you would like to use the Norton equivalent because it's easier to calculate. Whereas if you have a high impedance node like an op amp, you want to use the Thevenin's equivalent because it's easier to calculate that, right? All right. Okay, so next is the frequency response. And so let me, I think a lot of people probably didn't understand the question properly. So what I really wanted from this was, obviously this is a simple RC circuit, and if I let you write the equation, you'll write the equation in 2 minutes and be done with it. But in typical, when you're analyzing circuits, most of them are very complex that it'll be very difficult for you to do it. So usually what we do is we do it by inspection, right? So you derive the same thing by inspection because that gives you intuition. You know where the pole zero locations are. Then if your circuit is not meeting a certain spec, you'll be able to do that. So that was really the motivation behind this question, is that I wanted you to derive the Bode plot as well as just the magnitude, not the phase, as well as the closed form equation without actually writing the node equations, okay? And that's why I kind of led through you these three parts, because so if I gave you this high pass filter, this is a high pass filter, and I say, oh, find the transfer function. Like as I said, you obviously can write the equation, but usually you find the asymptotes. So what I mean by asymptotes is basically these three questions. So you say, okay, at DC, what's the value? And at DC, which is this omega equals to 0, what's the capacitor? Impedance of a capacitor, it's infinite, right? So capacitor is a short. I'm sorry, it's open. So if your capacitor is open, then your network is going to look something like that. Is Vs, this is open, and then you have the resistor R, and this V is 0 because there's no current flowing through this. So I times R equals to 0. This is 0. So V out over Vs equals to 0. So that's the first part of the question, right? Then you will say, oh, what's that infinity, right? So that'll be your second asymptote. So at omega equals to infinity, the capacitor is a short, right? And the inductors will be opposite. So if I had inductor instead, at DC this should be short, and at infinity this would be open. So you do the same thing with the inductor, but they're opposite. So now your equivalent circuit is going to look like this, right? And this V out is nothing but just equal to Vs because it just completely shorted to the output, right? So that's the second part of the question. The third is you're trying to find out, because there is one storage element, so intuitively you kind of know that, oh, there is one pole or a zero. I mean, the zero is obviously coming because of the open capacitor, but the pole is going to be one pole because you just have one storage element, you cannot have more than one. And the way you find out is you say, okay, it's going from 0 to 1, so what's the halfway point? So which we usually call in decibels the 3 dB point. And the halfway point is when what? The magnitude of the capacitor is equal to the magnitude of the resistor, right? So if this impedance here is exactly equal to R, then this V out would be just Vs over 2, right? So that's how you find out the pole location. And this is nothing but R is, I'm sorry, omega. This is at omega equals to 1 over RC. And then you go to the next part of the question. So from those three questions, I first wanted you to derive, plot the Bode plot, just the asymptote of it. And basically those three should have led you to plot this. Sorry, that's not what I wanted. Okay, so we found out that omega equals to 0, the output is 0, right? And then let's say this is the point where the transfer function is equal to 1. So at infinity, it is 1. And let's say this was a linear plot. I mean, linear axis, not log scale. It just somehow linearly going and joining. And we found out that this halfway point, so let's say this is half, is at 1 over RC. So that's your Bode plot. So it's a high pass filter with a pole at 1 over RC. So how do I find the closed loop transfer function? Now you know there is a 0 at 0. That means I need to have just a S, right, at equals to 0, because S minus 0 is a 0 at 0. And then some constant K, we don't know what that is, we'll find out. And then it has a pole, just one pole, right? And that pole, we said it's 1 over RC. So the only thing we need to know is K, and we can find that out by finding what this transfer function is at S equals to infinity. And we already know that. That's, V out over Vs, we said equals to 1. So at infinity, if you take this S divided by the denominator, if you just take the S and divide it by the denominator and do it at infinity, you'll just get 1 over S term here, which will go to 0. So you basically get K by RC. The K by RC is because this P1 is 1 over RC. That's at S equals to infinity. And we know this value equals to 1 from that previous calculation we did, which means that K is equal to just RC. So now we know the entire function. So it's S times K, which we found out RC. And the pole is at 1 over RC, so it's SRC plus 1, right? So this is, again, trying to find a closed loop transfer function by inspection without actually writing in the node equation. So like as I said, a lot of times when you're doing design, it'll be very impractical for you to write node equations, and you have to do it by inspection. You'll do it hierarchically. Sometimes you'll break the circuit into, a couple of pieces. So this is a tool we use as designers a lot, so it's something good to know. All right, so the second, the question 6, nothing fancy here. I just wanted you guys to know how to solve time domain equations for RLC circuits, or just RC or LC or whatever it is, right? Again, I think a lot of people got confused with this question. So one thing I think, well, actually a lot of people didn't even attempt this question, but one of the things which most people make a mistake is they cannot find the current I through it. But again, this is only one branch. That's only one branch here. So, and if this is ideal current source, then current through this is also I1, current through the inductor is also I1, current through the capacitor is also I1, because it has to satisfy KCL at every node. So you have that, right? So if you know the current going through it, for each element you can find out the voltage. So the first one, V, again, since the current is 0, and we'll assume all the initial conditions are 0, so it's 0 till, so let's call this position some T0 maybe, this is T1. So is it till T0, V1 is 0, because that's the voltage across the capacitor. If the current across the capacitor is 0, the voltage is also 0. Now you start ramping it up, and I sort of gave you some slope at which it is ramping, and if you just write, and V1 is nothing but the voltage across VC, right, which is just the integral of I over T dt, which is MT dt, and since we don't have any initial condition on it, then this is simply MT square over some 2C. The values are not important. What I wanted you to get is that, okay, it is a quadratic function till it gets to M1, T1, like that. And then, so this is from T0 to T1. From T1 plus, if you have a constant current source, right, it's just I naught, then it's just an integrator, right? So I won't write the equation, you probably know that. So it's just an integrator which just integrates, that's all, right? Now for V2 is nothing but V1 plus the voltage across the inductor, and the voltage across the inductor again, from 0 to T1 it is 0, there's no current flowing through it. And then from T0 to T1 it's L di over dt, and if this slope is a constant with some value m, then this is simply ml, right? So for V2, you're going to get 0, and you're going to get a huge jump, and that value is just ml. And then it's whatever capacitor value it is getting integrated, right? And then from T1 plus, VL is just 0, right? Because there's no voltage across it. So you get that, and then suddenly you get the jump back on, and then whatever is the integrator cap, you'll get that. But obviously in real circuits, you won't get jumps like this. There will be, either ringing or there'll be some slope, but for this question, that's all I wanted to get. So basically there are a couple of elements in this question. I wanted you guys to remember that if you're given an idle current source, your current is fixed, you just use that current profile. That's it. For every node, use that current profile. And then you just need to know the voltage across capacitors for a given current, or if a voltage is given, you need to know the capacitor current, which are pretty simple. But I have seen, I have interviewed thousands of people probably now, or hundreds of people, and they still get stumbled by this. So just have these fundamentals ingrained. If it doesn't come any help with circuits, at least it'll help you with your interviews. Okay, so this one, again, it's the same sort of principle that when you're doing AC responses, a lot of times you want to quickly know what kind of responses you're going for a different circuit. And you can know that from the location of the poles, right? So this is again a good sort of picture to have in mind. And I'll show you another picture which I actually got from Valkenburg. It gives you that picture. And I think a lot of people got this right. Well, about 5 people. But actually nobody gave a reason, but everyone drew the equivalent. So if you have a certain transfer function, let's say some h of s, and I'm going to just take like just two pole systems. Let's say you have S minus SB, and these are complex conjugates, and they always need to be complex conjugate for real circuits. And the reason for that is you'll see that when you write the time domain equation for this, the value needs to be real, so that's why they have to be complex conjugates. So if you have something on the j omega axis, then you need to have something on the minus j omega too. Now, one thing to remember is that and this is something, again, a lot of people don't realize, is that if you take a network, the time response, depending on where you take it, always depends on a combination of 0 and the poles. But the nature of the response always depends on the poles, and the pole never changes, doesn't matter where. So let's say you have a very complex circuit with 15 nodes. You take the response in 1, 2, 3, 4, 5 nodes. If the thing is oscillating like this, ringing, it'll ring everywhere. It's just that the magnitude will be different depending on the 0 of that location. Okay, so that's why knowing the pole where they are is very, very crucial. And usually when you have a system like this and you write the time domain, let's say I want to find the time domain of this, then usually it's something like k dot, e to the power sigma t, and this will be, plus minus j omega t, right? So, and this, if you do a Euler transfer from this will be sine omega t plus j cos omega t, j times cos omega, cos omega t plus j sine omega t, and that gives you the sine wave part of it, which you see in all these plots here. And this one tells you what's the damping rate, right? At what rate is it going down or going up? So if I, just take this and draw it, then you're going to get something like this, where you're going to get some ringing, and that's omega here. And this rate is directly related to sigma. And so if you know that from this pole, like for example, if you look at these two poles here, if the sigma part is positive, then this part is going to grow, right? Which means it's actually an unstable system. So that's this one here, right? So this is that S1. And for oscillators, they're always on the j omega axis because sigma is 0. So this is 1. Then you get actually just a plain sine wave. So that's this one here. So you get, that's your S2. And this one here, and you can see that I chose 2, where you can see one frequency is higher than the other one, which means that if you want to, you want to find out, oh, is it S4 or S3? Is the one which is higher up in the j omega axis, which is S3 here, so that must be S3. And you can see it's closer to the sigma axis, which means it takes longer to settle, so that must be S3. And this one is obviously S4, and that's S5 and S6, because omega is 0 for this one. There is no oscillation. It's just a plain transient. Like if you have a RC time constant, then if you give a step response, that will be for poles on the j omega axis. And if you probably done feedback systems where if you have a system of poles and you put a beta feedback, you will do the root locus. You'll take these two real poles and split it, and if your system becomes unstable, then they'll split it way far down here. If they're here, you'll get ringing. If they go on the other direction, it's so damped and so on. So it's good to sort of have a pictorial view of your pole location, because when you're designing feedback systems, you'll be always trying to find out what's your dominant pole, if it is complex conjugate, where the location is. So it's a good tool to have. So I had another slide which is just showing that picture. You can see that as long as you're in the sigma axis, there is no oscillation. It's just pure like RC time constant. As long as you're in j omega axis, it's a pure oscillation. And as you're going up, this oscillation frequency goes higher and higher. And then when you go to this part of the quadrant, it's a mixture of both. You have the oscillation decaying or growing if you're in this region, right? All right, so I think that was a little bit fast, but I just wanted to go through it really quickly, and then maybe we can. So I'm going to pause the recording so